Here we go again. So this time we're going to talk about pointer analysis, and we're going to talk about making more pointer analysis more precise by unleashing the power of selective context sensitivity. This is a paper by Tian Tan, Yue Li, Xiaoxing Ma, Chang Xu, and Yannis Smaragdakis. All right, we should talk about pointer analysis. Let's do that. Why do we want to do pointer analysis? Well, it turns out when you analyze object-oriented programs, then you have this thing, virtual call resolution, and you really need to do pointer analysis to do that. So here's a bit of code. And so you have class A, it has a method M, which returns 4. And you have class B that extends A, and it has a method M that returns 2. Now we have some code fragment that says, create a new B object and print what happens when you call M on it. And so what does it output? Well, if you look at just the a.m statement in isolation and you use something called class hierarchy analysis, then you're like, well, the declared type is A, so it could be an A, but it could also be a B because B extends A. And so you might say, well, it might be 2 or it might be 4. And then there's a lot of ways to be smarter. And the most general way to be smarter is by doing some sort of pointer analysis, and then you can resolve this virtual call to B, and you know that only b.m gets called and 2 is going to be output. The advantage to doing this, one advantage for performance, is devirtualization. And so virtual method calls are relatively expensive, although not as expensive as they used to be with dynamic virtual machines and all sorts of optimizations, but still not as cheap as static calls. And so if you know that the call to a.m is certainly calling b.m, then you can just replace it with a static call and it's basically instant. Otherwise, you might have to do a dispatch based on the type of the object. So it's like the question is, how many targets are there for M? All right. Another thing you can do is method reachability. So here we have the whole call graph of the program. And so we have the method a.m and we have the method b.m. And so the question is, in this program, I changed the new B to new A. And so here the question is b.m ever called? And if this is the whole program, then the answer is no. Only a.m is ever called. And so we can get rid of b.m. We don't need to analyze it, and everything's great. And we can do cast resolution. So we can say, look, you have this method, and you have a collection, and the collection says whatever. Then you get something from the collection. The collection, let's say that it has type collection of A, and you get a B from it. And again, we're assuming that B is a subclass of A. And so the question is B always a B what you get, or it could be an A? One way to do this is if in the program there's no instantiation of new A, this is an idea called rapid type analysis, then the answer is no. So what you want to do is you want to see, well, what objects get put into collection C, and then you use that information to deduce facts about what comes out of collection C. And that comes from the eventual instantiation site of this object. Okay, how do we do pointer analysis? So this is an extremely quick view of it. Basically, there's points to graphs. These don't look like graphs because I was too lazy to draw graphs for this talk, but they should probably be graphs. And so what we do is we can have a points to graph, depending on how we do it, for every point in the program. And so after program point 1, then we say A points to the object instantiated at program point 1. Then after point 2, A can still point to the object instantiated at 1, but then C can also point to the object, must point to the object instantiated at program point 2. When it gets more complicated is where we have B equals A. And so now we know that B points to the object that A used to point to. And so this is why it's a graph. B points to the object with A, and then A still points to where it used to, the object instantiated 1, and C points to the object at 2. And then we have B equals C. And so the question is, well, what does B point to? And that brings up the notion of flow-sensitive analysis. And so if we're analyzing this in the way that actually makes a lot of sense, but which is more computationally expensive, then we say that B points to the object that comes out of program point 3, as in it points to, sorry. We definitely know that after program point 4, it definitely points to C, but if we do a flow insensitive analysis, then what we're going to say is, well, we have both the B equals A and B equals C, and so we don't know which one runs last. If we're doing a flow sensitive analysis, then we definitely know that the object at program point 4, or the statement of program of point 4 runs last. And so we have this strong update of B, and it points to definitely what C points to. Otherwise, you might have to say that it can be what A and C points to in a flow sensitive approach. This is faster, but it's less precise. It turns out that in this paper, we're not going to talk about flow insensitive analysis at all, but in the other paper that does come up. So flow sensitive analysis is a good way to be faster at the cost of precision. Okay, the other thing you can do is context sensitivity. So the two big questions for pointer analysis are you flow sensitive, and which notion of context sensitivity are you going to talk about? I'm just going to talk about the easiest possible one. And so here, what we have is we have the method M, which we're analyzing. So it calls use of A. And then we have methods foo and fob. Foo is going to call M with method X, and fob is actually going to call method M with null. And so when you're analyzing the body of M, it matters which context you're being called in. Are you being called from foo, or are you being called from fob? If you're being called from fob, then you know that the parameter A is null. If you're being called from foo, you don't quite know that, unless you then go look at another level of context sensitivity, and then you look at bar, and that says foo of new A. And so if you'd have two levels of context sensitivity, then you can resolve this completely. And so the question also is, if you're being context sensitive, how far up the call stack do we look? Okay. The other notions of context sensitivity that have come up are object sensitivity and type sensitivity. I won't get into them too much because they're not super relevant to our paper, but I will say object sensitivity, we also consider the allocation site of the receiver object, which in this case for foo is O. And so we care about which this object we invoke on. Type sensitivity is a less sensitive variant of object sensitivity. Oops, wrong key, sorry. So the question is, how far up the call stack do we look? And the idea of this paper, many papers before it, but this paper pushes it even farther, is how far up the call stack do we look? And so we can be uniform, and we can say for all the program, we're going to look up the call stack 2 places. So we're going to be, level 2, context sensitive. But it turns out you can do different things for different places. And so you look for calls which you know to be not threats to scalability, and you do inline those. So you look deeper at those. And you also look for methods that you know to be important, right? There is a question here, which is, are you going to specifically include things you know are good, which is what you might do, for instance, for collections, or do you exclude things that you know are bad? And in fact, the things that we look at here include things that are known to be important. Okay, so that's a background about pointer analysis. Let's talk about this particular paper, having given the quick 10-minute background. The goal here is to produce precise pointer analysis results at the limit of scalability. And so selectively using more context sensitivity than before. And I guess I'll get into the next slide. But we're talking about hours long runtimes, right? Like it's saying, well, we're going to integrate these different pointer analyses, and we're going to let each of these pointer analyses run up to 2 hours. So that's the amount of time that we're willing to spend on these analyses. And so they have this meta framework called Unity Relay, and it combines extant context-sensitive pointer analysis. So it's like we have 3 analyses in this particular case, and we're going to combine them to get the best results we can get. with only a bit of worry about how long it takes. Okay, the schematic is you have your program P and you have, in this case, 3 approaches S, which we'll talk about in a bit. And so there's the unity approach, which is the more expensive approach, and it's use all the approaches in S. And so you maximize context sensitivity. If any of the S's say analyze a thing, then you analyze the thing at the precision that the approach says. So that's kind of expensive. And so you might use relay. And so what that does is, well, unity is too expensive. So we're going to do one analysis as it is, and then we're going to combine other analyses results and use multiple passes, but not make it too expensive. And we'll make this more clear in the later part of this talk. There's an implementation called Baton, which implements unity relay, and it integrates 3 analyses: collection, zipper E, and scalar. We will talk a bit more about what they do in the future. And they implemented it on 12 benchmarks, which they selected for being hard to analyze benchmarks, and have results from 3 metrics and 4 clients. The key idea of unity. Okay, so here's this thing about that hopefully we will have learned in 2020 or 2021 or 2022. Not everyone has learned this. And so one of the key models that you have to know in 2022 is that exponentials swamp linear growth. And so people complain, look, we should have more hospitals. And yes, we should have more hospital capacity, sure. However, if you have uncontrolled exponential growth, you are still in pain. And so if you have something that's growing exponentially, you're just out of luck. And pointer analysis can grow exponentially. In Unity, the goal is to be prepared to pay linear cost as a good computer scientist, but you want to try to avoid the exponential. We're not going to be, there are no guarantees about avoiding exponential. This is kind of empirical. So empirically, we will avoid the exponential cost, but it's still going to be expensive. Okay, so the observation is that the existing analyses try to push sensitivity as far as possible while being scalable, while meeting some, threshold amount of scalability, runs in 2 hours. And there's an insight from an earlier paper, which is that only a small set of methods hinder scalability. And so what we want to do is we absolutely want to avoid them. As it turns out, what we actually want to do is we want to select on things that are known good rather than avoiding. In this paper, there is no set of, danger methods, don't go here. But there is a set of methods that we do want to do. And so let's say we have analyses S1, S2, and S3. So S1 is going to say, I really care about X, Y, Z, and alpha. I've abstracted it a lot, but one of the ways I've abstracted it is we might say X has 3 object sensitive and Z has 1 type or whatever. But for the purpose of this example, we're just going to say S1 says X, Y, Z, alpha. S2 says get a lot of context for A, B, and X. And S3 says get context for alpha, beta, Z, alpha, and B, A and B. And so what the idea in Unity is to do the ones that show up in more than one analysis at the max precision. In fact, at the precision that is demanded by each of these approaches. And so it says do X, Z, A, B, and alpha at maximum precision. Okay, so here's an example of the Unity approach. It's a picture, and maybe I think that putting this after the specific things approach is actually a better way to show it. But here we have S1, which has this collection of methods, and it has this collection of methods at 2 object sensitive. And then the CI is everything else. So everything else is context insensitive. We don't care about context, whatever. Okay, for S2, what we do is we do another set of methods at 2 type sensitive. Okay, and then for S3, we're going to be fancy. We're going to say a small set of methods gets analyzed at 3 object. A lot of things get analyzed at 1 type, and then some things get analyzed at 2 object sensitive. And so in Unity, what you do is you compute the whole thing at the sensitivity level that is demanded by the most sensitive of any of the analyses, right? And so we can see that in that picture there. So yeah, if some sub-analysis says to do M, then the idea behind Unity is that it's probably not a scalability threat because the analysis S was shown as analysis that kind of works to some extent. And so if S says to do it, then we can probably do it and it's not going to blow up. And the other thing is use max precision on the overlap, right? So you do the thing that each analysis tells you to do, at least. Okay, this could be too slow. And so they propose another approach, unity relay. And so this time we run each of the analyses separately. So you do analysis 1, then you do analysis 2, then you do analysis 3. That is, you do the context-sensitive thing for the methods that are called for in analysis 1. So there's two sub-approaches in relay, relay O1 and relay O2. And in relay O1, you do sub-analysis 1, and you do only the methods that sub-analysis 1 says to do. However, you do them at the max precision that happens anywhere. And then in pass 2, you do analysis 2's methods that it says to do context on, but you do those at the max analysis. And then in analysis 3, you do the methods that analysis 3 says to do at the max analysis of anyone. And then there's this filtering. So you take the results from pass 1, and then you pass them on to pass 2. And then you take those results, and then you pass them on again to pass 3. So that's relay O1. And I think we'll see that, yeah, sorry, I should have switched the slide, but I didn't. This is relay O1. So it does maximum cost of any method. It only does the methods that are called for in any analysis at a time, but at some precision that might be specified by some other analysis. Okay, and the reason it's called relay is that it propagates points to analysis between different passes. So pass 1 runs, it computes its thing, and then it gives its results to pass 2, which then takes as input the result of pass 1 and then does its own computation. One thing I was meaning to say, or put on a slide, which I didn't say, is that call graph and points to analyses are also tightly linked. And so you're going to reduce the size of the call graph, which is going to in turn reduce the size of the points to analysis. So you reduce things, you reduce both potential calls as well as potential points to sets. And both of these things will help improve precision in subsequent passes. So here's another specific example. So we're going to do context insensitive analysis first. And so let's say that at point V, it computes the result O1, O2, O3. After you run pass 1, then it's going to figure out, hey, O2 could never happen. So the points to set at V is actually going to be O1, O3. And then what can happen is that pass 2 can benefit from the fact that pass 1 eliminated O2. So it might have taken that as input as a possibility. Now it doesn't have to. And so it can get better results in turn. Okay, the other variant, relay O2, is a no max cost variant. And so in this variant, all we do is propagate results between passes and reuse the native precision. So basically you're doing analysis 1 on its own, and that is just analysis 1 because it has no previous thing. The difference here happens when you do analysis 2. What you do is you start with the results that analysis 1 did. However, you do analysis 2 exactly the same as you would have if it wasn't as part of relay. The only difference is that it starts with a better answer about the world than the naive answer. And so you filter the results with what comes out of pass 1. And then in pass 3, what you do is you then take the results of pass 2 and you do pass 3 just exactly as you would have before. Right. So note that in this example, filtering versus intersection doesn't show up. So intersecting the results of pass 1 and pass 2 gives you the same results. In general, pass 2 can benefit from having the answers that it gets to filtered. And I think we see that on the next slide. We do. All right, so here we have some code and we do points to analysis on it. And so what happens here is that we have the context insensitive results. And so you can notice that across all the rows, A, X, and P are the same. Y, Q, and B vary. And so what happens here is that for Y, analysis S1 manages to prune the answers for Y down to O3 only. And for Q, S2 manages to prune the answers from O5, O4 to O5 only, right? And so if you take the intersection, then S1 and S2 will have the same results, as relay. So they both have O3 and O5, the more aggressive result. But if you pass the results along from stage to stage, then what can happen is that you can know that the set for B is actually empty. It is actually a null variable, and sometimes we want to do nullness analysis. And so the relay blocks the flows that are allowed in S1 and S2. And so it's going to say, well, when you get to program point 5, you know that the S1 answer is true, and also the S2 answer is true. So you know O3 and you know O5. And because you know O3 and you know O5, then you know that that object has to be null. And so it is more powerful than just doing these analyses separately and combining your results. It has some implications on performance too. Despite the fact that you're doing more work, you manage to avoid some of the expensive things. And so sometimes it is more quick to do the analysis, even if you're doing more analyses, because you don't do some of the work that you had to do. Okay, and so I talked about relay O1, where you do an analysis using the maximum sensitivity told by anyone, and then O2, where you use the analysis with its sensitivity, but then you combine the results from different phases. So you try O1 first, and if that's too slow, they don't say how you know it's too slow, then you use relay O2. You choose this on a pass-by-pass basis. Okay, so relay is better than any approach on its own, because you're just anything else you do is going to take more time, but it's going to give you better answers, and you're never going to get worse results. You're just going to potentially improve results. And in linear terms, it scales no worse than any constituent. Of course, if you have 3 analyses, then it might take 3 times as long, but it's not going to blow up exponentially. They point out that past ordering may have effects on results, and they have a paragraph discussing that. I admit that. Empirically, it has minor effects. Okay, there is some formalism, which I am not going to go into much, but I'll just say that they have basically 2 theorems for unity and 2 theorems for relay. The unity, well, the things have the same form. So first theorem is soundness. So PA unity S is sound. So that means that it has no false negatives. Any pointer, any alias pointer relation that exists in the program dynamically is going to be in the results reports. And then the second is a precision result. So it's at least as precise as any of the constituent analysis. And that intuitively makes sense. You're always combining results, and you're never going to get rid of anything that no analysis said that you should get rid of. So that's for soundness. And for precision, you're also not going to get more things, because you're going to get rid of all the things that any of the analysis said. For the relay, then we still have the soundness results. So again, no false negatives. But we also have a precision result, which is a bit more complicated. It says it's at least as precise as any of the constituent analyses. And also, after you run all of them, then the result is at least as precise as the result of the previous pass that you did. And this is true for both the O1 approach, where you used the specific context information that the most picky analysis would say, and also the other one where you just do the analyses and you combine results. So they have some evaluation. And so they use 3 components, which they try to get diverse approaches for. So there's collection, which is 3 object sensitive analysis on collection methods. So it's like, Java util list. It's like list.get. This is super important. So we're going to go three levels of object sensitivity on that. We have zipper, which is some principled precision loss patterns, some heuristics, and that chooses 2 object sensitive on selected methods, which are different methods from collection methods in general. And then there's scalar, which computes the object allocation graph and chooses 2 object sensitive, 2 type sensitive, 1 type sensitive, or context insensitive, depending on what the object allocation graph does. So different types of heuristics which do differently, and the idea is to combine them. They have 13 large and complex Java programs, so 13 hard to analyze programs from Da Capo, as well as benchmarks from more recent literature where 2 object sensitive fails to run in 2 hours. So the research questions they addressed in the evaluation are: how scalable and precise is unity? And also, if unity doesn't work, then can we use relay? Okay, they have tables. I can't show the table on the slide, there's too much. But basically, the result is that for unity, all the sub-analyses meet the time budget. They were kind of chosen that way. And then Baton manages a 12 out of 13 on time budget. There's one that doesn't fit. It's not always slower, is what they say, and they point out it's faster than all of the benchmarks, all the other component benchmarks on two benchmarks, Gallian and Soot, including the context-insensitive one. And then it's faster than at least one of the benchmarks on 5 of the 13 results. So sometimes, despite doing more work, it still does better. The flip side of that, which they do not mention, of course, is that it's slowest on 8 of 13. And sometimes it's 2 times slower. It's linearly slower, but it's, 2 times is still a lot. There's a May alias graph here. And so we can see that, the last column does do better. The thing about that is that you can reduce May alias sets a lot, but sometimes they don't matter. And so they, of course, have to run it on clients too. If there's no clients, you should be suspicious of the results. They did not compute how much faster it is on the clients, and their table is kind of large, so okay, but they kind of should. So I kind of looked at it and I computed results. And so it does 20% better at best on showing that casts are always going to succeed. And then on reachable methods, it gets rid of 0.3 to 6% of reachable methods. So it does a bit better. It's not like doubly better, but it has modest improvements at potentially up to twice the amount of runtime. So we talked about unity, and now we're going to talk about relay. How scalable is relay? So the idea is to crank up the precision of zipper E and scalar until unity times out. So they actually try to hit the 2-hour time limit. And then they combine the analyses using O1 when possible and O2 when not. And so there's 3 phases. There's a collection phase, the zipper phase, and the scalar phase. And so collection runs in about the same time as context insensitive. Zipper E runs in about the same time to 2x slower compared to running on its own. And scalar runs mostly 2 times slower and sometimes 3 times slower. I think that is a total runtime. I don't remember for sure, and I think the paper is not super specific about that. So it's 3x slower, I think, including zipper in particular. Collection is usually kind of fast. In terms of precision, we again have this May alias thing, and here they show relative numbers. So in this case, it gets rid of like 70 to, or it has 70% as many, which is good, to about 82% as many results as collection, the base case. Or the base case is actually bigger for Eclipse, but it does better. And when you look at the clients, it's not super awesome. It does like 15% better on FCAS and up to 0.7% better on pcalls and R methods. And the question is it all worth it? So you pay a constant factor more time. The alias analysis results are significantly better. Clients benefit a little. And in terms of overall evaluation of this paper, I think, look, it's kind of a niche. You're trying to make alias analysis better. It's a useful niche. People need to do that. In terms of client results, you're paying a lot of time, and the engineering trade-off in actually deploying this would be hard to justify. But in terms of looking at this as research and how you can integrate analyses, it's interesting to know that you can do that. And so that's a lesson that's worth looking at. But I wouldn't necessarily say it's practical per se. All right, good. We will talk about this tomorrow. See you then.